Okay, so chapter 5 is called Discrete Probability Distributions. If they are discrete, what does discrete mean? And my first person is Cynthia Hamlet over at Starmont. Maybe, maybe not. We can't hear yet.
Values that can be counted.
Good. Okay. Absolutely. Values that can be counted. So we're going to specifically look at things that we can count and then their probabilities. Okay? And we're going to put them together in a distribution, and then we're going to tie together how to find the mean, the mean, the standard deviation, and the variance. Okay? So we're going to look at some kind of interesting connections between what we've been doing with the statistics and then our new stuff with a kind of idea of probabilities. There are 4 sections that we are going to cover in this chapter. We will be doing all of them. We're going to talk about just probability distributions in general, mean, variance, and standard deviation. Then we'll specifically go into how to do binomial distributions. And then these other types, we have a couple of other types within that. Okay, so that's just kind of our overview so you know where we're going. Okay. A probability distribution, again, reminder, these are review words, so you don't necessarily have to write them down, but a random variable is a variable whose values are determined by chance, okay? A variable, right? Random variable. So we're going to use that word. What are random variables? They're determined by chance, so we might talk about rolling a dice, and one of our random variables might be rolling a 1. It's determined by chance, whether or not we get that. And then the big one that you want to write down here is our definition of discrete probability distribution. Okay, so I'll read it and then I'll let you write. It consists of the values of a random variable that can assume, and the random variable can assume, and the corresponding probabilities. So it's a distribution that's going to have the values of the variable and then their corresponding probabilities. That's the best way I can kind of summarize that. And this last bullet should be review. See if you can read that and agree with that one. I don't want to hear about it. Was Mr. Steppen still in there?
No, it was just Miss Noble.
I have some smackdowns to do today.
I wasn't in there, so don't yell.
Okay, rolling a dice. This is what an actual probability distribution looks like. So when we roll a dice, you write in the first row or column, whatever you want to do, all of the outcomes. So the outcomes are x's. These are random variables. When we roll a dice, what random variables can we get? A 1, a 2, a 3, a 4, a 5, or a 6, right? And then their corresponding probabilities go right underneath of that. So the probability you would get a 1 is a 1 out of 6. Probability you're going to get a 2 is 1 out of 6. 3 is 1 out of 6. And what do all these probabilities add up to? 1. Okay? So those add up to 1. Now, they don't always look this nice. In other words, the probabilities aren't always all the same, right? So sometimes we know when we have certain situations, the probabilities are different. And the one that I love is constructing the probability distribution for the sum when rolling 2 dice. Okay? I'm going to add in a slide here. On this slide, we're going to construct a probability distribution for rolling 2 dice. Okay? But this time, instead of going horizontally, I'm going to go vertically just so that you know it can go either way. All right? So we're going to make a table going this way because this is the way I like to do it in algebra. I don't like horizontal ones. I always go vertical. The left column is my x's. So what are my random variables when I roll 2 dice? And when you're playing a game, you're always doing the sum of the 2 dice. So what's the lowest we could get when we roll 2 dice and you add them up? What's the smallest number? Michael?
2.
Okay, 2. And then obviously I can roll a 3 and a 4, okay? And all of these different ones, I want you to go all the way up to whatever the highest number is and then stop. Pretty sure it's 12, double sixes, okay? Now, in the second column, we're going to put their probabilities. So what's the probability of each of these things happening? Now, throughout your last chapter, you've had to figure out the probability of some of these different ones, okay? Let's first of all think about how many total outcomes there are here, and it's not 12, it's not 11. Each of these don't have 1 out of 11 chance, okay? We need to go back and think about our sample space. How many total outcomes are there when you roll 2 dice? Alexandria at Starmont.
36.
Okay, good. So all of these probabilities need to be out of 36. And each of them have different weights. Now, the chance that you're going to roll a 2, that's snake eyes. There's only one way you can get that. That's rolling a 1 and a 1, okay? So this has a 1 out of 36. But all of these have different probabilities. They're not all 1 out of 36 because we have to add up to 1. 12 is double sixes. There's only one way you can get that, and that's to actually get double sixes. So that's a 1 out of 36 chance. But now I want you to think through and fill in the rest of these, okay? If you need to look at the sample space, that's fine. But think about how many ways could you get a 3? How many ways could you get a 4? What are each of these corresponding probabilities? Okay, I'm going to give you about a minute to fill that in. Okay, Jordan, how many ways could we get a 3?
2.
2 ways, a 1 and a 2 or a 2 and a 1. All right, Sadie, a 4.
3.
3. All right, Caitlin, a 5.
4.
4, a 1 and a 4, a 4 and a 1, a 2 and a 3, a 3 and a 2, right? And we're going to continue this pattern. Some of you have got it all filled in rather than wasting all of our time. This goes up to 5, and then the highest probability is to get a 7. There's 6 ways to get a 7, okay? A 3 and a 4, a 4 and a 3, a 2 and a 5, 5 and a 2, 1 and a 6, 6 and 1. And then it comes back down, okay? So 6, 5, 4, 3, 2, 1, okay? And I got all mushed in here, but you get the idea. So this is kind of a fun probability distribution. I like it. I just think it's kind of neat the way it turns out. If you add up all of these numerators, you should get 36. So 36 out of 36, which is a whole. Okay? So that's kind of a fun one. So this is the sample space. Or I'm sorry, I said that wrong. The probability distribution when rolling 2 dice, and it's actually for the sum of 2 dice. So x, our variable x, we're defining that as the sum of 2 dice. 2 6-sided dice. Shoot, that wasn't what I wanted. Okay, so here's one. If we were tossing coins, represent graphically the probability distribution for the sample space for tossing 3 coins. So remember, when you toss 3 coins, you could get head, 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 tail, head, tail, head, tail, tail. Remember, we've written this out a couple times, right? Same thing for if you have 3 children, boys and girls, boy, 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 girl, girl, boy, girl, boy, girl, right? And there was a total of 8 outcomes. Do you remember when we did that, right? So there's 8 outcomes. The chance that you're going to get no heads is a 1 out of 8. That's only when you get tail, 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 right? So if I needed to, I could write out the whole sample space over here. It would be like head, 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 tail, tail, head, head, right? You guys, etc., etc. The chance that I'm going to get no heads would be when I get all tails. That's 1 out of 8. The chance that I get 1 head, that was either getting head, tail, 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 head, tail, or tail, tail, head. That's 3 out of 8. 2 would be 3 out of 8, and all 3 heads is 1 out of 8. What does that add up to? 8 out of 8. 1 whole, right? Okay? So this is a true probability distribution because this adds up to a whole. And this is what we could do for a graph. Okay? So we could have the number of heads and then each of their probabilities as a bar or just a vertical line, right? So it would be a representation of what we have for each of those probabilities. So on the x-axis go our x values, and on the y-axis is those probabilities, or p of x's, or our y values, right? Okay? So we have each of our probabilities there. Now, these are the crazy formulas that they want to give you to find mean, variance, standard deviation, and expectation, which expectation really is the same as mean. It looks like a bunch of Greek, right? It kind of is, okay? This is a Greek letter for mu, this is sigma, this is x, p of x. So you multiply them, add them all up. That gives you your mean, your variance. You got to do all this crazy stuff. Your standard deviation, this. Next slide, okay? Forward. How many of you think you would be much more comfortable with just in list 1 put all the x values? In list 2 put all the probabilities, right? Or the frequencies. And then what do? Run one variable stats, list 1, comma list 2. Why would this be nice? Because our calculator will give us the mean, right? Okay? So just like before when you did a weighted mean, right? And you had a list 1 and a list 2, it's the same thing. What's our mean going to be, or our expectation? When we run one variable stats, which number is our mean? The x bar number, right? The very first number in the list. What's our standard deviation? And I put sigma sub x. It's this one. Sigma with the little x. And because we have the entire population, we have everything in that sample space. And what's the variance? You take the entire standard deviation number and square it, okay? So you take this number here. Yeah, I got cut off. Okay, and you square it. I'll go back to that. Just give it one more second here, okay? So remember that this is not a hard thing to do. You don't have to follow those crazy formulas, okay? If you want the mean, you just run your one variable stats and you find it, okay? So this should be kind of a combination or review of the sections that we've done. You have a probability distribution, you have their probabilities. The only difference is in list 2 before we always put like numbers. We put frequencies, right? Okay. But now in list 2, I realize that. In list 2, what are you going to be putting? The probabilities, okay? So the x values go in list 1 and the probabilities will go in list 2.